Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We're at lecture 8.2. We will be going over C++ AMP advanced concepts. The objective of this lecture is for you to understand more advanced features of C++ AMP programming model. And we're going to go over explicit device memory allocation and copy. And we're going to go over asynchronous or overlapped host accelerated execution. And then we're going to discuss some useful features of array view to support multi-dimensional data arrays. So here is a situation where if we wanted to explicitly manage device memory allocation and data copy, C++ AMP does allow us to do that. And the default use in C++ AMP or intended use of device memory is through array view. If you use array view, then in the parallel for each construct, the compiler will automatically generate the device memory allocation and copy for you. And this will make your code more future-proof as well, because there are more and more fusion-style devices where CPU and GPU actually share the same physical memory. And in that case, the compiler can actually generate, instead of generating the device memory allocation and copy, the compiler can simply generate a remap kind of instruction to allow the CPU and GPU to even communicate even more efficiently in those devices. So in even some of the even more future devices, the CPU and GPU will have pretty much unified virtual address space. In that case, the CPU and GPU no longer need to even have some of the remap kind of instructions. So using array view will typically make your code much more future-proof and portable to future device architectures. However, if you really wanted to manage the data, memory allocation and data copy on devices yourself for performance reasons, for whatever reason, C++ AMP does allow you to do so. So here is the vector addition example where we use, instead of using array view, we use a construct called array. And this is also a template in the C++ AMP. And then we see the copy statements. And in the parallel for each, instead of automatically capturing the values for A, B, and C in the accelerator, we're going to capture the pointers. So these variables are actually captured by reference, meaning only the pointers to those variables will be passed into the device. And then after the function, we're going to have an explicit copy of C back into the host. So here are some important points that we can summarize about the explicit memory allocation and memory and copy management. The first one is array construct is similar to array view construct, but with two important differences. The first one is that the array construct will allocate device memory for, so this is implied. Whereas array view is simply another way of accessing the host structure. So in devices that require extra memory allocation, the compiler will do that for you implicitly. Whereas if you use the array construct, it really instructs the compiler to allocate a device memory for you. And the second one is array. Any variables that you declare with the array construct, there will be no association with host data. Unlike array view, where every array view variable is really just another reference, a way to access an existing data, host data. So that's why the array view has to associate the newly declared variable with not existing host data. So you can actually compare array construct to CUDA malloc. So that's the closest equivalence between C++ AMP and CUDA. The second one is the copy function. So the copy function receives two parameters. One is source and one is destination. The source and destination can either be host or device memory. And this copy instruction really is very comparable to CUDA memcopy. So this is to explicitly instruct the compiler to generate the copy operations into the device or back into the host. The third point, important point, is that array variables are captured by reference for lambda expression. And keep in mind that the array variables are really allocated on the device. So they are really explicit memory allocation for device. So that's why we really cannot capture the value from the host and send them to the device. But rather, the only reasonable way that we can have the parallel for loop statements to access these variables is just to be able to access their pointers. So through their pointers. So that's why the host code is passing the pointers to these device allocated memory variables into the parallel for construct. So then in the end, when we have an explicit copy of CA back to C, we actually implicitly synchronize host and device. That's why the host will automatically wait for the completion of the kernel and copy the CA back, data structure back. So we no longer need to have that explicit synchronization as we have seen in the array view example. The next important part is the host accelerator execution timing. When we use, let's say, array view, we have essentially the execution of the host to be copy and copy A, copy B, and then we will execute the kernel, and then we'll copy C back. And whether we use explicit copy or array view and let compiler generate the copy, the execution timing is pretty much the same. And during this time, whenever we will not have the option to be able to execute anything after that copy request. So there's sometimes we would like to be able to have the CPU or the host to be able to execute some activities. Once we requested a copy, we know that the host, the device will eventually copy the data back, but we would like to use that window of time to be able to execute some host activity. And in CUDA, this is essentially an asynchronous kernel launch and device copy. And remember, we have these CUDA device synchronization events that allow us to have the host to execute some activities, and then we will explicitly synchronize. C++M allows us to do something similar, and in many ways in more elegant manner. So this is the code where we took from the array view example, and then after the parallel for each, we're going essentially we would originally we just have a synchronization. However, if we wanted to be able to execute more activities until we really need to, we run out of activities and we really need to wait until the copy of C back to the array, then back to the host, then we can do an explicit synchronization. So this is accomplished with the completion future variables. So we can declare a completion underscore future variable, which is a C++M type. And we can declare a variable, in this case, it's called done. And then we can take the cv.synchronize underscore async method. And this essentially gives us a synchronization event that would allow us to explicitly synchronize with the completion of CV activity in the host code. So we first derive an event, and then we can actually just do all the other processing that we want to do on the host. So all this other processing code is going to be able to continue to execute. And once we have run out of all the things that we needed to do on the host, we can go and use the done variable, and then we use the done.get method to explicitly synchronize with the completion of CV. So this will force us to wait until the copy of C back into the host and before the function returns. So this allows us to have a very elegant way to continue to execute on the host while the device is working on the kernel and eventually copy back before the two has to resynchronize with each other. So this gives us a summary of execution timing where we can do these other processing on the CPU, even though implicitly we're requesting that copy, but all these activities will just happen on the side with the copy and compute on the device, and then eventually we just use done.get. And when the copy completes from C host, a copy of C completes from host device to host, the done.get will complete that synchronization, and the host will then be able to continue to execute the subsequent activities. So this brings us to the last advanced feature of C++M that we're going to cover today. It's the multidimensional array view. So far, we have introduced array view as with one-dimensional examples, but the array view is actually even more useful, more important for multidimensional arrays. So let's go into the matrix multiplication example where we're passing m and n into input arrays into the function, and we're going to be generating the p matrix. And the width is assuming that we have a square matrix multiplication. Obviously, you can change it to the rectangular matrix multiplication with additional input parameters. So this is just for simplicity of the example. So we can generate an extent object, and the extent object dim will have two dimensions. So this is really the size of the matrix in the x dimension and y dimension. And obviously, if we have a rectangular situation, we will have different values in each dimension. And then we can generate an array view that takes the input m array, and we can declare an array view of 2 dimensions, and this floating point value, and it's constant, meaning that this is an input value into the kernel that will not be changed. And we declare that as a d underscore m, and then we can use the extent that we just declared dims as the extent of this array view. So this will define the size of the 2 dimensions of that dm, and then we associate this dm with m. So now we have a 2-dimensional way of referencing or accessing m elements. We do the same thing for n, and then we can actually declare also the variable p, array view d underscore p for the product. So we still have the dp underscore p discard data, meaning that this is output, so the existing value in the p doesn't matter, and then this will prevent the compiler from copying any of the existing p data into the device. So within the parallel for each construct, we can actually just access d underscore m as a 2-dimensional array. So now we see that we have the x index and y index listed as 2-dimensional index. And this makes the C++M code much more elegant than the C code or CUDA code, because now we can access these 2-dimensional arrays with 2-dimensional indexing format. So this allows us to declare extent variables for 2D and 3D extents. So here we show a 2D example. It should be obvious for you to be able to generalize into 3D situation. And we also showed how the array view for 2D and 3D arrays can be declared and used. And you should be able to easily extend this into a 3-dimensional case. So one of the interesting and useful features of array view is we can use it to project a 2D array view into a 1D array view, or in some cases we can project a 3D array view to a 2D array view or even 1D array view. So here we show the matrix multiplication, and we still showed the part of the code where we declare dm and dn. But now let's assume that we wanted to be able to access one of the rows of the M matrix. So we can actually declare another array view, which is a one-dimensional array view called d underscore m underscore row. So this is essentially an additional way of accessing M, essentially accessing one of the rows of M. And so then we can just initialize this array view by assigning dm row. And this row needs to be generated. So we have dot, dot, dot here. But if you go back to the matrix multiplication, you will see that we can generate the row according to the variables. So we can just use whatever you have there to generate that variable before you use it. And then now in the parallel for each construct, we can just go ahead and access d underscore m underscore row with the x dimension variable, the x dimension index. So this is really equivalent to the previous code, but we're now using a row view of a two-dimensional array. So we can easily access a plane of a three-dimensional array as a two-dimensional array using this kind of projection. So this completes all the interesting and useful advanced features of C++ AMP that we're going to cover today. As it turns out that this is not a complete coverage of C++ AMP. This is really just to get you to give you enough conceptual understanding of C++ AMP in order for you to do the optional lab with C++ AMP. And there are still several other important features, but since you're not going to be likely going to use those features in the lab, we're not going to spend the time to describe those features. But those features will include device query. You can actually use C++ AMP and still query the kind of devices you have in the system and take the right actions. And you can also have explicit usage of accelerators. You can designate the particular accelerator that you want to use to execute your code. And for those of you who are interested in those features, you should read C++ AMP specification, or just go to textbook chapter 18, where we will have more detailed description of all the features that we have described in the lecture, as well as those advanced features that we did not have time to cover. Now you have you are ready to do the optional bonus lab assignment with C++ AMP. Thank you.